Hello, this is Mr. White, and this video is on series, aka sums of sequences. And specifically, this is an extra video on finite geometric series. At least as I record this video, we've covered finite geometric series in class, but I noticed that I believe some students could use some extra examples, so here it is. Let me show you the two examples we're going to do, just so you can decide whether this is useful to you. The first example will be asked to write in sigma notation the following series that you see before you, and also actually calculate the sum. Notice that you're not told how many terms there are, you're just given the first few terms and the last term, and you have to figure out how many terms there are. In the second example, it'll be the same idea, write in sigma notation, calculate the sum, but in the second example, you'll be given the number of terms. Okay, so example number one, write in sigma notation. We should be pretty comfortable with the idea of sigma notation, that I'm going to put k equals 1 down here. That would usually be my default choice. And remember, it's the explicit rule that goes right here. And for a geometric series, which this is, it will be in the form of a times r to the n minus 1, or since I decided to use k, I'll say k minus 1. All right, so what is a in this case? Well, a is the first term in the series, so a is going to be the 567 in this case. So let me erase a and put 567. What is r? Well, the series is getting smaller. I'm multiplying by a fraction less than 1, and it doesn't take too long to determine that r is 1/3 here. Be careful, a lot of students will accidentally put 3 there and think, oh, I'm dividing by 3 as I go from one term to the next. But remember, at the common ratio, you have to say, what are we multiplying by? Well, dividing by 3 is the same as multiplying by 1/3. All right, I also need to figure out what is this upper bound up here. So if this is a sub 1, if the first term is a sub 1, and this is a sub 2, and this is a sub 3, this last term is what we'll call a sub k. Actually, you know what? Let me call that a sub n, where n represents the number, the upper bound up here. All right, well, that's where my explicit rule will come in handy. A sub n, according to my explicit rule, needs to be equal to 567 times 1/3 to the n minus 1. And if I know that my a sub n term is also equal to 7 over 65/61, then I can solve for n now. I've now got an equation where I just need to solve for n. All right, so notice this is an exponential equation and the unknown is in the exponent, so that should be our first hint there that logarithms are going to come into the picture. Remember, before I use the logarithms, I've got to divide out the 567 there. I've got to get it just in the form of something to the something power equals something else. Can't have anything else in it. So let's divide both sides by 567. And before I grab the calculator, I'm just going to write this, and this is going to get a little bit messy. I don't think any problem that you see in your assignment nor on my test will be any messier than this. But I'll do 7 over 65/61 divided by 567. I'm not going to bother simplifying that yet. I feel like I'm on a roll, and I'd like to go ahead and get the logarithm into the picture. So we'll say log base 1/3 of that ugly fraction within a fraction, 7 over 65/61. And obviously it's your choice. If you wanted to try simplifying that fraction in the meantime, you could. But that's what equals our exponent, because logarithms are exponents, n minus 1. So you know what I'd like to do here? Just maybe it seems a little bit lazy, but I'm going to go ahead and do 1 plus on both sides. 1 plus. And now I've got n all by itself. N equals this rather nasty logarithm, but at least I'm ready to grab the calculator and figure out what that is equal to. And I'm expecting a whole number. If I don't get a whole number at this point, I know there's a problem, because n has to be an integer. It's a sub n, and that subscript has to be a whole number. So let's do, the way I'm going to calculate this I could try to calculate it all in one fell swoop, but I'm going to use my change of base formula. And I'm going to say log of 7, let's do a parentheses, 7 divided by 65, 61. If you have TI-84, you could use the fraction capabilities, but I'm going to type this as if I had a TI-83, divided by 567. And I'm going to say that's enough right now. Let me just, so I got a negative number. So remember the change of base formula, I'm doing log of 7 over 65, 61 over 567, divided by log of 1/3. That's just my change of base formula. So I've done the numerator. Now I'll say divided by log of 1/3, the denominator. And I get 12. But remember, I've got to do the plus 1 and get 13. So now I know that there are 13 terms in this series. I hope I didn't go too quickly, but I'm trusting that you're reasonably comfortable with logarithms and other basic topics as we really delve into the series aspect here. So that's 13. That tells me that I can scroll back up a little bit, and that 13 is what goes into my sigma notation. All right, so there it is. There's the sigma notation. Now let's actually calculate the sum. And I need to remind you that writing this in sigma notation is a completely different skill than calculating the sum. So for calculating the sum, I'm just going to drag this down and let's kind of start fresh here. And interestingly, to calculate the sum, if that's all I'd been asked to do, if I didn't have to do sigma notation, I wouldn't have bothered finding out how many terms there are, because believe it or not, you don't even need to know. Let me show you why. For calculating the sum, I'm going to say that all these numbers add up to some number s. And as long as I know what my common ratio is, my common ratio in this case was 1/3, I can proceed to say that 1/3 s equals 567 times 1/3. Well, that's what gives me the 189. 189 times 1/3, that's what gives me the 63, and so on. Whatever my second to last term was, that's going to give me 7 over 65, 61. And then that last term will give me 7 over 65, 61 times 1/3. That's the same as just putting an additional 3 times in the denominator. All right, so why did we do that? Well, here's why. Because if I say I'm going to take this top row and subtract the bottom row, if I'm going to take this top quantity and subtract the bottom quantity, on the left-hand side, I clearly get s minus 1/3 s. And I'm going to go ahead and write it out the long way. I'm not going to bother simplifying it. Equals, and then when I look at the right side, if I do this entire top row minus every single quantity in this bottom row, almost all those terms are going to cancel out. The 189 in the top minus the 189 in the bottom will cancel out. So will the 63s and all the numbers in the dot, 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 all the way up to 7 over 65, 61. And really, there's only 2 terms that did not cancel out. The original 567 did not cancel out. And then that final term that ended up in the bottom row. Now remember, I'm subtracting that bottom row. Whoa, I just noticed I wrote 566, didn't I? Not sure why that happened, but minus that final term in the bottom row. So that's 7 over 3 times 65, 61, which is the same as 19,683. Let's go ahead and factor the left side. All right, and finally divide by that 1 minus 1/3, and I would get s equals 567 minus 7 over 19,683 all over 1 minus 1/3. Now the reason I didn't bother simplifying some of this is because if you compare this to the formula that's in the book, which is something like a times I'm going to, well, 1 minus r, and then here would be something like 1 minus r to the n. If you compare that to the form in the book, you can kind of see the similar structure. And that's the only reason I didn't simplify the bottom. I really wanted you to see how this just reflects the formula that the book shows. But I'd rather you really understand why or how we're coming up with an answer rather than just using a formula. So now that we've come to this point, again, this is where we would grab the calculator. And let me bring it on the screen here. And let me just move this over a little bit. And I would do, I'll go ahead and use the fraction capability here. Sorry, TI-83 users. 567 minus 7 over 19,683 over 1 minus 1/3. I'll go ahead and just type 2/3 into the calculator. And I get 850.499. Or 0.499 if I round off. So on my paper, I'd say that approximately equals 850.499. I'll say approximately equals, clearly I'm rounding off. And that would be my final sum. And notice that I didn't really need to know how many terms there were in order to do that. All right, let's do the second example. All right, write in sigma notation and calculate the sum. This one's going to be a little bit easier because I'm given the n value. I don't have to go to any work to do that. So the sigma notation, sigma, k equals 1. The n value is 15. I don't have to do any work to figure that out. This is definitely geometric, and this is a times r to the k minus 1, since I'm using k. And hopefully you're getting the hang of that and you feel like that was pretty straightforward. Clearly I'm multiplying by -4 to get to the next term every time. Now as far as actually calculating the sum, sort of same idea here, except we need to know what the last term is. So to calculate the sum, you really do want to know what the last term is. So the fact that n equals 15 is a pretty nice clue. Because if I take my explicit rule and then ask what's the 15th term, it would be 5 times -4 to the 15 minus 1. And I'm not going to bother to put that in the calculator at this point. I'm simply going to write s equals 5, minus 20 plus 80, ... all the way up to 5 times -4 to the 14th power. I'll go ahead and simplify that. Again, similar to the last example, I'm going to go a little more quickly since it's the same idea. I'm going to multiply by the common ratio. So -4s in this case. 5 times -4 would give me -20. So even though I have a negative common ratio, the same process still works. That would give me 80. ... The second to last term would give me 5 times -4 to the 14th. And then this last term would give me 5 times -4 to the 15th. All right, scroll down a little bit. I'm going to imagine that I'm taking this top row and subtracting the bottom row again. So s minus -4s, be careful of those double negatives. S minus -4s equals top. Again, we're doing the whole top. Actually, let me clarify this. Whole top row minus whole bottom row. And most of them will cancel out. Let me point out that it doesn't really matter whether you do the top row minus the bottom row or the bottom minus the top. As long as you're consistent, it doesn't really matter. The result comes out the same. And this time I'll get 5 minus. So I think in the last example, I think I had done something equivalent to the bottom row minus the top row in this example. But again, don't really worry about it as long as you're consistent. What you don't want to do is do like top minus bottom over here and then bottom minus top over here. That would not be good. All right, so factor out on the left side, factor out the s, and I've got 1 minus -4 here. And then here I'll go ahead and factor out a 5. and I'll get 1 minus negative 4 to the 15th power. If I divide by the 1 minus negative 4, let me go ahead and be a little bit lazy and just use the same line. So if I divide by the 1 minus negative 4, gets rid of it over here. And again, the reason I'm not simplifying it is because I want you to see very clearly where the book's formula came from. This is the formula for the sum of a geometric series in the book, and you see term for term there that it matches what we've come up with on our own. All right, so grab the calculator, and let's calculate that. I'll do the fraction. 5 times 1 minus, be careful again with the negatives. I'll do negative 4 in parentheses raised to the 15th power. And again, at negative 4 to the 15th power, I can tell that's going to be a big number. 1 minus negative 4, and that is our answer. A big number which roughly matches my yearly salary in millionths of a penny, perhaps. There we go. That's our final answer. All right, hope you got the hang of it. Hope that was helpful. If you're interested in trying a couple on your own, give them a shot. All right, here are the answers. Here's the answer to the first one, and I'm showing the logarithm that was used to find the n value in this case. And finally, the second one, right there. Notice that we got a negative answer in this one. If that surprises you, let me give you a little quick insight. For this particular one, the common ratio was, let's see, negative 6, right? So if I take each term in Excel, and if I say each term is the previous term times negative 6, and then I say in this column I'm going to make the sum of this column. Notice that when I take just add the first two terms, I get a negative sum. Notice that when I add a third term in there, it becomes positive. When I add another negative term, it becomes negative. And hopefully when you look at those individual terms that I'm adding each time, you get an understanding of why this sum keeps flip-flopping. And in this case, we just happened to go to 8 terms, so we ended up with a negative sum.